Modified atmosphere packaging. Let's get into it. Now, I want you to remember the last time that you went to the grocery store. As soon as you stepped in, you would see the produce that looks fresh and mostly without blemish. It is an absolute wonder as to how the produce we constantly consume on a daily basis is always ready at a moment's notice inside of these grocery stores. Then, when we decide to possibly buy a product, it may go bad quickly depending on how we store it. One of the main reasons for produce looking the way it does inside of these grocery stores is because of the gases used on the produce to both enhance or slow down this ripening process of fruits and vegetables. So then, what if we decide to take this one step further and put the produce in bags or containers to further control the gas concentration around the fruit or vegetable at all times? This particular technique is called modified atmosphere packaging, or MAP for short. MAP is a technique that has been used since the 1930s and is still very much valued today. But how does it work? How effective is it? Is it necessarily required? What are some downsides to it? There are many more questions to be asked, along with many more answers to come today. Okay, now let's get into the mechanism of MAP. Say you have a piece of broccoli on the table. Despite it being chopped off from the source of growth when taken out of the ground, it still respires like you and me. Broccoli takes in oxygen and releases carbon dioxide when respiring. The equation for the respiration goes as follows. Carbohydrates plus oxygen yield carbon dioxide, water, and energy. This breathing will eventually lead to the death or senescence of the broccoli. To slow this respiration process, we will actually place the broccoli inside an airtight bag to reduce the amount of oxygen in the surroundings over time. In MAP, this new barrier adds an additional layer of protection from not only the atmosphere, but also other possible factors that may negatively affect the broccoli, thereby extending the shelf life. This method of protection is also relatively inexpensive due to the plastic material constantly being used in MAP. Now that we've done this, a new problem arises. Because all the oxygen has been used up, as well as the carbon dioxide has built up in high concentrations, there is now an imbalance inside this closed system. Our research has shown that high amounts of either carbon dioxide or oxygen can lead to a physiological change in a product. High amounts of carbon dioxide can cause a number of different defects in the product. Carbon dioxide starts to build up, and the container is now filled with it and has no oxygen, which will eventually lead to the death or senescence of the product, along with a rotten smell, textures, and flavor. Similarly, in open air, too much oxygen can also lead to different defects, such as mold growth, oxidation, off flavors, and more. That being said, having these two gases in the ideal concentration can lead to a positive outcome. Carbon dioxide, on one hand, has a bacteriostatic effect when applied due to its high solubility in water, creating carbonic acid, which lowers the pH, inhibiting the growth of bacteria. Carbon dioxide also slows this respiration of produce, extending the shelf life when in an elevated amounts. Oxygen, on the other hand, can inhibit the growth of anaerobic bacteria, but also promotes the growth of aerobic bacteria. Along with this, it can also promote the oxidation of lipids and more. So in order to avoid anaerobic bacteria, as well as oxidation, you must generally have a low amount of oxygen. Therefore, we can summarize that to make the best gas composition, you will generally need an elevated CO2 level and a low O2 level to extend the shelf life. This margin of what the percentage of what both gases should be at is different for all fruits and vegetables. Nevertheless, this trend of how low oxygen and higher carbon dioxide leads to a longer shelf life is true for all. Okay, so now we know what happens when you place broccoli in both open air and in a closed system. So then, what if you decide to add very small holes into the packaging to allow for a relatively small amount of carbon dioxide to escape, as well as a small amount of oxygen to come in? These small holes are called perforations, and they can very much vary in size. This heavily affects the gas composition inside the container as the broccoli respires. The more holes we add, the more gas movement there will be. Therefore, to find the ideal gas composition to extend the shelf life to its maximum length, we need to test and compare the qualities of broccoli over time, when each is under different amounts of perforations. This is all due to the concentration gradient being the main driving force here, pushing the gases to fill these areas where the concentration is not equal. Now, with all the explaining of the mechanism out of the way, let me show you a possible experimental design that we have come up with to understand more of the effect of MA on broccoli. Let's discuss all the variables that will be in this experiment. The independent variable here will be the amount of perforations placed on the film. We will try 1, 2, 3, and even 4 perforations in duplicates to make sure our results are consistent. The size of these perforations that we will be using will be around 110 micrometers, so very small. That being said, this then means our dependent variables will be the gas concentration of both carbon dioxide and oxygen over the course of a couple of days. We will also measure some of the qualitative features of the broccoli to see when the broccoli falls out of customer acceptance range. We will be measuring these qualitative variables based on the look, the smell, the texture of the broccoli, and compare it to the fresh store-bought broccoli to tell when the tested broccoli is out of the acceptance range. Our materials for this experiment will go as follows: 8 impermeable plastic containers, 8 different impermeable films that have perforations ranging from 1 to 4, 800 grams of broccoli, an OxyBaby CO2 O2 headspace sensor, 8 septum stickers, 2 small temperature sensors, and electrical tape to cover some of the perforations. Now that we've set the stage for our experiment, let's see what became of it. Here's our data after an experimental period of 5 days measuring once per day. The groups here are color coordinated to allow for easy recognition of said group. Red being 0, orange being 1, yellow being 2, green being 3, and blue being 4 perforations. While we can analyze the data here, let's visualize the data so we can see things clearer, that being the gas composition. Here are our oxygen averages over the 5-day period, with the x-axis being in hours and the y-axis being in oxygen percentage. While all the data may seem relatively close to one another, let's take this one step further and look much closer at the last 3 days. Here we can notice a few things. There's a visible gap between all the perforations, showing that there is an effect on the MA even with these small perforations. Another thing is that their perforations actually do not change the oxygen percentage linearly. Rather, one can even say that the effect might look sigmoidal or exponential. This is because of the many different factors that actually influence MA. Factors such as headspace concentration, temperature, weight of the broccoli florets, microbial growth, permeability of the container, amount of perforations, humidity levels, respiration rate, gas composition outside the container, and so much more. Basically, a ton of factors that can affect the MA. This makes it very hard to actually calculate the amount of perforations and the size of said perforations needed for a certain container and produce to extend the shelf life as much as possible. This can be done through constant trials, but is often hard to find. Next, we look at the change over time of the carbon dioxide levels and see a similar trend of a non-linear change throughout the testing period. This time, the curve can look somewhat logarithmic in that the more perforations added start to level out the amount of carbon dioxide that can be in the container. The examples here are not actually good at showing the extension of shelf life, since the carbon dioxide levels are way too high, as well as the oxygen levels being way too low. Our research has shown that the oxygen should be around 2 to 3%, give or take, and the carbon dioxide should be also around 10 to 15%, constantly to ensure the extended shelf life of the broccoli. Now let's look at here, set some visuals of the broccoli over time. Here's our group 0B, and the pictures were taken 24 hours into the experiment and 96 hours into the experiment, respectively. Now in this situation, we remember that this group has no perforations, therefore all the oxygen would eventually been used up. What does this mean exactly? When referring back to the equation for respiration, When the broccoli runs out of oxygen, it can no longer create energy for itself, causing it to die. This leads to microbial growth, off odors, and yellowing, which puts it out of this customer acceptance range. We see this yellowing a little bit in this 96-hour picture. Now, let's look at some other groups with perforations in them. Here's group 3B, and again, with the 24-hour picture versus the 96-hour picture. And because of the perforations, we do have oxygen present in the system, which can give way to one thing: mold. Mold has a few criteria when it comes to its growth. Of course, as stated, mold requires oxygen. Mold can grow at any percent of oxygen, meaning that it could have grown in any of the groups that had perforations on the film. Another requirement for mold is the actual food source for it to grow, which obviously here is the broccoli itself. Temperature, along with humidity, would be the next two on the list, as it would need a damp, warm environment to allow for growth. This is done through the room temperature the broccoli was placed in, as well as the humidity actually being produced by the respiration of the broccoli. And the last requirement are mold spores, which are actually ubiquitous in the environment, so it is actually very hard to track where they are, so it's best to just prevent them from growing rather than stopping the spread. When we then look back at group 3B, we actually see this mold present within the package, showing that all these conditions for mold growth were met. Similarly, in group 4A, we see the exact same thing, except in higher amounts. There are more deformities that occur when an unwanted MA happens, but these are just some that display themselves under these created conditions. Modified atmosphere packaging is a very useful and efficient technique that has been used for a long time. We see this constantly being used in industry as well as retail to ensure that the product given to the consumer is at its peak quality as much as possible. It can have many different looks as well. Although we focused on the fresh produce side of MAP in this presentation, this type of food storage is used in packaging deli meats, cheeses, and even frozen products. Within this video, we have covered perforated packages. But what about permeable versus perforated packages? Or even permeable packages with perforations? The science and technology behind finding the proper packaging for each individual food product is more multifaceted than just simply adding perforations. It has to do with gas diffusivity, temperature, film material, and much, much, much more. We hope this presentation was a good introduction to the world of modified atmosphere packaging and has got you more curious about what it takes to not only store food, but preserve its quality for as long as possible. Thank you.